Today we're diving deep into quantum superposition. You guys sent in a ton of fascinating stuff on this, and honestly, I'm still wrapping my head around it.
Yeah, it's definitely one of those concepts that challenges how we normally think about reality.
It's like, imagine being in multiple places at once. Sounds crazy, right?
Yeah, in our everyday world, that's impossible. But in the quantum realm, totally different story.
That's what we're here to explore today, from the basics to some of the really weird implications. I mean, just reading through this research, I kept thinking, how is this even possible?
Well, let's start with what quantum superposition actually is.
Perfect, because one of the articles defined it as a system being able to exist in multiple states at the same time. It's just how.
It's almost like a video game character being able to walk and jump at the same time.
Until we, the players, decide what happens next.
Exactly, and that's kind of how it works with quantum systems.
So in our world, things have definite states, like a ball is either red or blue.
Right, but in the quantum realm, things could be a lot fuzzier. It's not that we just don't know the state until we look.
It's that it's actually in this blurry mix of possibilities.
Exactly, until we try to measure it.
And that's when things get even more interesting. One of the things that came up a lot in the research was the idea of a qubit. How does that tie into superposition?
A qubit is like the quantum version of a bit in classical computing.
Okay, so a bit can be a 0 or a 1, but a qubit.
A qubit can be both 0 and 1 at the same time, thanks to superposition.
So I keep seeing this analogy of a coin spinning in the air, heads or tails, but it's not decided until it lands.
Exactly, and that's a good way to visualize it, but this qubit's both at once quality, that's what makes it so powerful.
Okay, I'm starting to see how this gets us closer to building those super powerful quantum computers we hear about.
Exactly. A single qubit being both 0 and 1 opens up the possibility of doing calculations exponentially faster than any classical computer.
It's like exploring every path in a maze simultaneously instead of one at a time.
That's a great way to think about it.
But how do scientists even represent this mathematically? Some of the stuff in these articles, woo, pretty intense.
Well, one way is through this formula. Give equals A's plus E1 says.
I'm not going to lie, that looks a little intimidating.
I know, it could be a bit overwhelming at first, but let me break it down.
Please do.
So the say represents the superposition state. The 0A and 1 say, those are the basic states, kind of like our heads and tails.
Okay, got it. And what about those Greek letters, the A and A?
Those are called probability amplitudes.
So they tell us how likely we are to measure the qubit as a 0 or a 1.
Exactly, and here's where it gets even weirder. These amplitudes can be complex numbers.
Meaning they have both real and imaginary components. That's where my brain starts to melt a little.
It is pretty funny blowing. And this leads to phenomena like quantum interference.
So it's not just about probabilities, there's this whole other layer of complexity with these complex numbers.
Precisely. And it all affects how these quantum states interact.
So this superposition thing, it's not just some theoretical quirk. There are real-world applications.
Oh, absolutely. We're talking quantum computing, cryptography, even incredibly precise measurements using quantum metrology.
Hold on, quantum cryptography. That sounds straight out of a spy movie.
It kind of is. It uses superposition to create communication protocols that are fundamentally secure.
Like impossible to eavesdrop on?
Pretty much. Because any attempt to intercept a message would actually change the quantum state, alerting both the sender and receiver.
Okay, that's way more secure than any password I could ever come up with.
Right. It's some next-level stuff.
But let's get back to the basics for a second. One of the things that really hooked me was the double slit experiment.
It's a classic.
It seems like the perfect example of superposition in action.
It really is. Imagine shooting electrons one by one at a barrier with two slits. Logically, you'd think they go through one or other.
Yeah, that's what I'd expect.
But here's where quantum mechanics throws us a curveball. Instead of two distinct clumps of electrons behind the slits, what you get is an interference pattern on the screen.
As if each electron went through both slits at the same time.
Exactly.
So even a single electron can be in multiple places at once. It's defying the very laws of physics as I know them.
It definitely challenges our classical intuition. The double slit experiment shows how a single electron can be in a superposition of going through both slits at the same time.
And then its wave-like behavior creates that interference pattern.
Exactly.
Okay, that's just wild. But wait, doesn't observing them force them to choose a single path?
That's the heart of the measurement problem. Before we look, the particle is in that blend of possibilities.
But when we measure it, the superposition collapses and it becomes a definite state.
And that's one of the biggest mysteries in quantum mechanics.
So the act of measuring somehow affects reality. That's where things start to get philosophical.
It really is, and it's a question that has puzzled physicists for decades.
I'm already feeling like my brain needs a reboot.
I hear you.
But there's another concept I want to dive into, and that's entanglement. The research mentioned it as almost a superposition, and it definitely piqued my curiosity.
Entanglement is where the strangeness of superposition gets, well, even stranger.
Okay, I'm ready for that rabbit hole, but maybe after we let all this sink in a bit, my head is already spinning.
Take your time. It's a lot to process. But yeah, entanglement, we're just scratching the surface there.
Okay, I think I've rebooted my brain enough to tackle entanglement. Last time we left off with this idea of two particles being linked, even across huge distances.
Yeah, it's definitely one of the most mind-boggling concepts in quantum mechanics.
I mean, how is that even possible? It feels like we've wandered into science fiction.
It kind of is like science fiction, but it's real. And it all comes back to that shared quantum state we were talking about earlier.
Okay, so we talked about single particles being in multiple states at once, but now we're talking about multiple particles being connected.
Exactly. It takes the weirdness of superposition and, like, dials it up to 11.
Okay, I need an example. My brain needs something to latch onto.
All right, imagine two coins flipped at the same time, but instead of being independent, they're magically linked.
So if one lands heads, the other is guaranteed to land tails.
Exactly, even if they're miles apart.
Okay, that's weird, but couldn't that just be a trick, like they were pre-programmed to have opposite results?
That's a good point, but it's different with entanglement. It's not about preset outcomes. It's about this deeper connection, this shared quantum state.
So the particles are in a superposition together, and that shared state is what creates that spooky correlation.
Precisely.
So it's not like they're sending signal to each other faster than light.
Nope, not at all.
It's like the information about their connection was baked in from the beginning.
Exactly. It's all about that initial entangled state.
So to really understand this, do we need to look at the math?
Well, one way to illustrate this is to look at a specific entangled state called the singlet state. One of the articles you sent uses this equation to represent it. SAID equals 1AB.
Honestly, that looks a little like something out of a physics textbook.
I know. Equations can be intimidating, but stick with me. It's similar than it looks.
Okay, I'm trusting you.
Basically, it's describing a system with two particles, A and B. Each of these particles can have a spin, either up or down.
Got it.
The equation tells us that if we measure particle A and find its spin up, particle B instantly becomes spin down, and vice versa.
So it's like they're two sides of the same quantum coin.
Exactly. The outcome for one is linked to the other, no matter how far apart they are.
Okay, so how do we even create these entangled particles in the first place?
There are different techniques. One common one uses a special kind of crystal. It splits a single photon into two entangled photons.
It's like taking a single coin and somehow splitting it into two coins that are forever linked.
Yeah, that's a good analogy.
So now that we've got these entangled particles, what can we do with them? What are the real-world implications of all this?
Well, entanglement is actually at the heart of some pretty incredible technologies. Things like quantum teleportation.
Wait, teleportation, like beaming ourselves across the galaxy, Star Trek style?
Haha, not quite. We're not teleporting matter, just information.
No beaming up anytime soon.
Maybe not yet. But the potential is still incredible. Imagine secure communication networks where information is transmitted instantly, unhackably.
That's thanks to entanglement.
Exactly. It's a game changer.
So if entanglement is so powerful, why aren't we using it everywhere? What are the challenges?
Well, one of the biggest is something called decoherence.
That sounds familiar.
We talked about it earlier, remember? Quantum states, they're incredibly fragile. Any interaction with the environment can disrupt them, causing that entanglement to break down.
So it's like building a house of cards in a windstorm.
Exactly. The slightest disturbance and poof, it's gone.
So how are scientists trying to overcome that? Are there ways to shield those quantum systems from the environment?
Researchers are working on that. They're developing techniques to create more stable entanglement. It's a constant battle, but the payoff could be huge.
Okay, so we've gone from single particles in superposition to multiple particles linked across huge distances. But what if we go even bigger?
You mean like macroscopic objects?
Yeah, like a baseball. Or even a person. Could we put those into superposition?
Well, that's a question that really pushes the boundaries of our understanding. We know quantum mechanics works in the microscopic world, and we have general relativity for gravity on a larger scale.
But unifying those two, that's one of the big challenges in physics, right?
Exactly. It's like the universe is playing by two sets of rules, and we're trying to figure out how they fit together.
And how does that relate to macroscopic superposition?
Well, one of the key questions is whether gravity itself prevents large objects from being in superposition.
So maybe there's a cutoff point where gravity becomes dominant and forces those superpositions to collapse.
That's the idea behind some theories. It's like there's a cosmic sensor preventing macroscopic objects from exhibiting quantum weirdness.
So no cats that are both dead and alive, no people being in two places at once. Because gravity says, nope, Not going to happen.
That's the gist of it. It's still a big open question, though, and physicists are designing some very clever experiments to try and test this boundary between the quantum and classical worlds.
I can't even imagine designing those experiments.
It takes some serious ingenuity, but the results could be groundbreaking.
All this talk about macroscopic superposition, it really makes you think about the philosophical implications.
Oh, absolutely. It raises some big questions.
If the universe can exist in multiple states at once, does that mean there are multiple realities out there? Are we just one possibility among many?
Those are questions that delve into metaphysics.
So there's a universe where I chose a different career path, a universe where I had a different breakfast this morning.
Some interpretations of quantum mechanics, like the many worlds interpretations, suggest exactly that. Every quantum measurement causes the universe to split, creating different branches.
It's like the universe is constantly branching out with every quantum event.
It's a pretty mind-bending concept, I know, and there's no scientific consensus on whether it's actually true or not, but it does highlight how quantum mechanics forces us to reconsider our very notion of reality.
I think I need to sit with that for a while.
Haha, understandable. But hold on, because we're not done yet. There's one more thing I want to introduce you to. The research mentioned something called generalized quantum mechanics, or GQM.
GQM sounds like we're about to go even deeper down the rabbit hole.
Exactly. GQM is where we start to push beyond the standard model of quantum mechanics. We're talking modifications to the theory that could lead to even stranger forms of superposition.
So it's like quantum mechanics on steroids.
You could say that. We're talking about some pretty wild ideas here.
Give me an example.
Well, for instance, some GQM theories suggest that probabilities, which in standard quantum mechanics are always between 0 and 1, could actually be negative or even greater than 1.
Wait, negative probabilities? That sounds like breaking the rules of math.
It does, doesn't it? It's a very counterintuitive concept.
What would a negative probability even mean in the real world?
That's a great question. It's like saying there's a negative chance of rain, or that an event is more than 100% likely to happen.
It doesn't make much sense in our everyday experience.
Exactly. But remember, these are just theoretical possibilities. We don't have experimental evidence to support them, at least not yet.
But even the possibility is mind-blowing. It makes you wonder, are there entire new types of superposition out there just waiting to be discovered?
That's the exciting part. GQM opens up a whole new realm of possibilities.
What else does GQM suggest? Are there other strange possibilities we should be thinking about?
Well, another fascinating area of research is how superposition interacts with gravity. We've talked about the challenges of putting large objects into superposition, but what if gravity itself plays a role?
So gravity isn't just a force. It's somehow influencing the very nature of quantum states.
That's the idea. It's a really deep question, and we're still searching for answers.
How could that even work?
Well, some GQM theories suggest that the gravitational field might be able to measure quantum systems.
So gravity is acting as an observer.
In a sense, yes. It's as if gravity is constantly observing the universe, preventing those macroscopic objects from showing their full quantum weirdness.
So gravity is like the ultimate cosmic observer, keeping things in check. But wouldn't that mean our understanding of gravity is incomplete?
Exactly. And that's why exploring GQM is so exciting. It challenges us to rethink our most fundamental assumptions about the universe. It encourages us to consider possibilities that might seem completely outlandish at first.
Okay, my brain is definitely feeling the strain. We've gone from entangled particles to negative probabilities to gravity as a quantum observer.
I know, it's a lot to take in, but we're just getting started. There's one final area of exploration I want to introduce you to, and it deals with the most fundamental question of all: the role of consciousness in quantum mechanics.
Consciousness. Okay, now we're really going down the rabbit hole.
Haha, you can say that. But it's a question that has fascinated physicists and philosophers for a long time.
All right, I think I need a moment to process all this before we dive into the mysteries of the mind.
Take your time. It's a lot to digest, but I promise you this next part is going to be a wild ride.
Okay, I think I'm ready to tackle this whole consciousness thing, but honestly, it's a bit intimidating, even after everything else we've talked about.
Yeah, it's one of those topics that always seems to spark debate, even among physicists.
Well, we've talked about how measurement collapses a superposition, forcing a particle to choose a state. But what exactly is a measurement? Does it need a conscious observer to make it happen?
That's the million-dollar question. The traditional Copenhagen interpretation, it says the act of measurement causes the collapse, but it's kind of vague on what counts as a measurement.
So does it have to be a scientist with a lab coat and fancy equipment? Or could it be like a stray photon bouncing off a particle?
That's the debate. Could a simple interaction with the environment be enough? A lot of physicists think so. They say consciousness plays no special role.
So our consciousness isn't what's collapsing the wave function.
According to them, nope. They argue that interaction with the environment, regardless of a conscious observer, is enough to cause decoherence and collapse that superposition.
So even without conscious observers, the universe was never really in a pure superposition state. It was always collapsing and recollapsing.
Pretty much. Creating the classical reality we see around us.
Okay. That makes sense. But I know there are still some people who think consciousness is fundamentally linked to quantum mechanics. What's their argument?
Well, they point out that consciousness is the only thing we know of that can directly experience quantum effects, like the collapse of a superposition.
So they're saying that suggests a connection. Because we can experience it, maybe our consciousness is somehow involved in making it happen.
That's one way to put it. Others think maybe consciousness itself is a result of quantum processes in the brain.
Whoa, okay, now that's getting a little out there. Are we talking about a quantum soul?
Haha, let's not go that far. It's important to remember these are pretty speculative ideas. There's not a lot of scientific evidence to back them up.
So most neuroscientists think classical physics is enough to explain how the brain works.
That's the current consensus. But, that's what makes quantum mechanics so fascinating. It constantly pushes us to reconsider our assumptions about the universe and even about ourselves.
Well, I think that's a great place to wrap things up. We've covered a lot of ground today, from superposition and entanglement to GQM and even the mysteries of consciousness. My brain is officially full.
Haha, mine too.
It's been an incredible journey, and I feel like I've got a whole new perspective on quantum mechanics and all its weirdness.
It's been a pleasure diving into this with you. It's always exciting to explore these mind-bending concepts.
And to all our listeners, thank you for joining us on this deep dive into quantum superposition. We'll be back soon with another episode of another mind-bending topic to explore. Until then, keep questioning, keep exploring, and never stop being curious about the universe and our place in it.